Hi, Rhonda and Catherine. I finished my experiment and got the data, and I have I have one bad news, but I have more good news. Okay, so first, the bad news is, um, regardless of how careful I was trying to be, I still got some anomaly in my data set. So I got an anomaly at two places. Uh, so first one is here. I got about 7 data that are abnormally high, and then it's over here. So this 7 data is about worth half an hour's data, and this is worth about 2 hours. 2 hours of data here. That's abnormally high. Okay, so that's the bad news. And if Catherine also had some anomaly in her data, I'm totally down for doing the experiment again for another 3 days. Um, and because now is the good news. First of all, I know exactly what happened that got me those two anomalies. So the one on the left is because I brought the weather sensor outside from my house, right? So the weather sensor was actually in room temperature. So that's why you see this drastic decrease in temperature when it suddenly was brought into the cold night. So I really should have just left the weather sensor outside before I started it, right? So to avoid this in the future, I'll just leave the weather sensor outside. So it's going to be the same temperature at the environment when I turn it on. Okay. And this part on the right, it's really funny. Um, it happens around like at 10 o'clock, 10 p.m. on 31st, starting from, yeah, sometime around that, 31st. So on that day in the afternoon, I was talking to Catherine about the battery is gonna run out, right? And Catherine said, like Rhonda, you gave her like a portable charger to charge the weather sensor. I was like, that's a great idea, right? So I also like dug out I have a portable charger as well, and then I did the same thing. I hooked up the portable charger with the weather sensor. However, I did it at night around 10:30 p.m. I even have a video because I was trying to record the process as well. Uh, where's okay here and wait here. So you can see I set up the weather sensor outside my garage, and there is a big window in my garage, like just on the outside of my garage. And since I did this, I tried to hook up the charger on the weather sensor at around like 10:30 p.m. It was dark outside, so I turned on the light. You see the light from the garage, and I'm highly suspecting, I'm almost certain it is those light that is like the radiation from it that's heating up the weather sensor. So the same effect as it's exposed to the direct sunlight. It's just instead of sunlight here is the from incandescent light, a light source, and it take the weather sensor about 2 hours to go back to normal. And also, I was outside for quite some time because I was trying to tape up the charger on the tripod over here, and I just also did some like chores. So I left that light on for quite some time, and I think that's the reason that's causing the about 2 hours of anomaly over here. Okay, the second good news is So we can totally be upfront about that on the blog or in the Catherine's research paper. But the second good news is, if you think about it, we get 72 hours of data, and this in total is like a 2.5 hour of data normally. So that doesn't really affect the data set as a whole much. And in fact, for our calculation, like we mostly just will be doing the means, right? Those anomaly really don't matter, and I will show you why. Like I think I'm lucky that those anomaly didn't happen at the time of the maximum and the minimum temperature of the day. If it happens at the maximum minimum temperature of the day, like um, normally it happens like a 3-4 p.m. right, the maximum, then that's gonna be a lot more trouble. Okay, so I'll show you why. Because when we calculate the daily mean temperature, there are normally two ways. So the first way is you just take all the data, right? Then you do the average. And the second way is you take the daily highest and the daily lowest, and then you add them up divided by 2. Basically, get the average of the high and the low. So the two methods, the results are actually quite similar. So you can use either one. I'll actually show you. So let's say I'm gonna just get rid of the first 7 data. Like it's really, because I know it's abnormal, right? So I don't have to use it, and it's only half an hour. So I'm just gonna start from, this is about 30 minutes past the 12 o'clock on 30th. So that's the start of my day, and the end of my day is here, right? So just 1 minute past the 12 a.m. on 31st. So this is a day's data. And then I'm just gonna use the statistical tool here. So I'm first gonna select the this portion of the data, and then I'm gonna get minimum, maximum, and mean. Okay. All right. I don't know if you guys can see this. I'll zoom in a bit. So the minimum is 2.599487, basically 2.6, maximum 11.92, the mean is 6.83. Okay, so maybe I'll just write it somewhere here. So the minimum is basically, I'll just round it to 2.6, maximum is 11.92, mean is 6.84. Okay, so this mean here is the average of all of the data, which is the first way to calculate the average. So that's fine. But the second way to calculate average is just to take the maximum and the minimum, add them up, divided by 2, plus 11.92, and divided by 2. And in fact, with this, we get 7.26. Right? You can see it's really close to 6.84. So those two values are like 5 or 6% difference. And if you do the second day and third day, I'll show you in a second, it's an even smaller difference. So like for my data, when I do the daily mean calculation, I can just use the maximum and the minimum value, add them up, divided by 2 to get each day's mean temperature, which is basically similar to you average all the data. But because I have anomalies, right? So if I use the max, and the anomaly doesn't happen at the maximum and the minimum, So I think it makes more sense if I use the maximum and minimum value, right? And like Catherine, you can use the same method, right? So we're consistent this way, like we're using the same method to calculate mean between BC and Ontario, right? So that's just the suggestion. And then I'll show you the second day. Okay, so the second day, I'll just move this data a little bit forward as the starting of the second day. And then I think it ends somewhere here. 1 minute past the midnight. Okay, so the second day starting from here, ending from here. And this part of the data is due to the light bulb, right? And so, but theoretically, it should be, because according to the other graph we get, this should be a smooth transition, which is also like the correct physics. It shouldn't be like abrupt change. There should be a smooth transition, and then so it should be something like this, right? So instead of this peak, however, that doesn't really matter because still the high will happen here, the daily maximum, the daily minimum will happen here, right? So I just need to get the maximum here and the minimum here by doing, just drag this window here and maybe make it a bit longer. A little bit longer, maybe a little bit smaller. Right, right. So as long as I get the that I get the maximum and minimum in this box, I'm good, right? I don't need to use anomaly data because it's not going to be the high or the low. Okay, so for this one, the mean is the minimum 2.6, maximum 15.47, and the mean is 8.6. Okay, so again, I'm gonna calculate the mean temperature using the second method, which is 2.6 plus 15.47 and divided by 2, and I get 8.89. And the other way to get mean is this mean here, right? 8.6. You can see 8.89, 8.6, they are even closer than the first day. So really, we can just take the maximum, minimum, then divide by 2. Okay, which is also like a convention many countries do. Some countries even do like 3-hour average, like they take the reading every 3 hours. So there are 8 readings during the day, then they just divide by 8, right? So there are actually many ways to calculate the means, but they all end up pretty much the same or similar, and they all represent the average temperature. And as long as like you are consistent on the method you use, right? And similar with the third day, but you get the idea. So this is one of the calculations we can do regarding the daily mean, and I think another thing we can look at, like you can do the same with Ontario data, and then we can compare our daily mean. I think for my data in the past 3 days, the average, like 3-day average is about 8.9. I think 8.86 to be exact. So you can like get the 3-day average for Ontario, and we can compare. Like you can get just the daily average for each day, then divided by 3. Okay. All right. The other thing we can look at is the relationship between temperature and the relative humidity. Um, I'll add the axis of relative humidity, and you can see they are exactly negatively correlated, which means when one increase, when temperature, like relative humidity increase, temperature decrease. When temperature increase, relative humidity decrease. And this is no surprise because I talked about the relationship between temperature and relative humidity in one of my videos, um, especially in BC. Now, this is the interesting part. I always observe this where I am in BC. So if you can take a look at your data in Ontario, see if temperature and relative humidity has this kind of relationship. It makes sense because relative humidity is basically the actual amount of water content in the air divided by the maximum amount of water the air um, can hold, right? So when, for example, when you increase the temperature, when the air get hotter, it can hold more water vapor. So the denominator, which is the maximum amount of water vapor the air can hold, becomes bigger, right? So when the denominator becomes bigger, and if your numerator doesn't change, the value, the entire fraction becomes smaller, right? Which is why when temperature increase and the denominator becomes bigger, the uh, air can hold more water vapor, and then the relative humidity will decrease. Uh, and you can tell this is based on the condition that the actual amount of water content in the air doesn't change much, and this can be shown by the dew point, right? Because dew point is actually uh, like related to absolute humidity, which is basically the actual amount of water content in the air, which is the numerator. And when dew point doesn't change much, then the actual water content in the air doesn't change much. The numerator doesn't change. Um, and if you look at the dew point change, need to add, okay, let me add the dew point. All right, so the brown one is the dew point, and the blue is the temperature, and the relative humidity is the green one. Now I put them on another scale so that you can tell the dew point is actually almost flat compared to the temperature. The temperature is up and down still, but of course, relative humidity will have the greatest amplitude because it's on a much higher scale, is in percentage, right? But but the point is, the dew point is not changing much, right? So the actual amount of water vapor in the air doesn't change much, but uh, the denominator, which is affected by the temperature. When the temperature increase, the air can hold more water vapor, and so the relative humidity will decrease. That's why you have temperature and relative humidity as inverse proportional or negatively correlated. Okay, so that's something like you can also look at with your data at Ontario. Okay, so another thing we can look at is actually the Environment Canada data. Um, okay, I think it's only for past 24 hours. There might be archived data, but I just haven't got a chance to search for it. So I just got the data for April 1st. And then, yeah, I kind of forgot to take a screenshot of their data for 30 and 31st. But we can just look at one day for April 1st and see how consistent the data are between the Pascal weather sensor and the Environment Canada data. And because I have some anomalies, right, in my data on that day, especially early in the morning. Let me get rid of the other two variables. Right, so I have some anomalies in the beginning of April 1st, right? So I'm trying to use data a little bit away from that. So I'll actually use after the data after 7 p.m. Sorry, 7 a.m. Yeah, somewhere around that. So I will be using this part of the data and compare it with Environment Canada's data. And this is my result. It's actually quite impressive that how our data is consistent with Environment Canada's data. Oh well. So this is the time on the left on April 1st, the first column. Don't know if you can see it. Right, so the first column is the time. And the second column is our data from the weather sensor. And the third is the Environment Canada data. And I think we can just plot it. You see it's actually quite nice. First of all, you can see the difference is really small, like within some part within 1 degree, some part is about 1 to 1.5 degree. But what's more impressive is the general trend, right? You see the two waves, they match almost perfectly, where environment, like this Pascal, the blue one, and the Environment Canada is the orange one, and where they peak together, like they have the crest at the same place, and then they have the chow at the same place. So it's actually, yeah, I think the data is pretty good considering this data from the Environment Canada is not at my exact location. I'm at North Surrey. This data is at White Rock because they don't have data everywhere. They just have data in a few locations, and I have to choose the closest one. So it is about 30 kilometers at least from where I live. So considering that, this, I think the weather sensor did a pretty good job measuring the temperature. Pretty consistent with the Environment Canada's data. Yeah, so those are some of the analysis I'm thinking about. So, and I'm interested in knowing what it looked like in Ontario. Please let me know if you have any other ideas. Thank you.